So here's the board powered up with the two 24-volt transformers. But it's 24 from here to here, and it's 24 from here to here. This is what I said it would be earlier. I did add two little diodes in here, and one hidden down here. As far as the heatsink goes, I made a little tiny, at least I think it's little. I think these are number 2 screws. Drilled in with a 16th inch bit. This is the 317. The leads weren't long enough, so I guess I have some thermal fuses there. And the heatsink. The other heatsink is here. And you can see I've chewed away at the fin. I didn't take the whole fin out, but to make way for the screws. Well, I have this here. Here's one of these little mounting boards that mounts over here. The daughter board will fit here. If you really look closely, you'll see that this is another board. I've constructed a second board. I have a temporary resistor plugged in here to bias or adjust the voltage of the negative supply. The positive supply is being varied by this potentiometer. Right now I have them both set to 9 volts. I have a current of slightly less than 1 amp. Output's 18 volts. And the next thing I'll do is build the daughter board. I started fabrication of the daughter board. Now this is a standard 4 by 6 centimeter perf board you can buy on eBay or whatever. The circuit board has a hole here. It's got 5 mounting holes. The corner mounting holes are not electrically connected. This one, however, is connected to the ground. I drilled a hole to mate with that. Actually mates like that. And you can barely see them, but there are the circuit board holes on the board. Now this 8-pin wire wrap dip socket has, see this round barrel here? Then it turns into a flattened piece of metal. I enlarged the holes in the what's to be the daughter board in order for the wire wrap socket to fit perfectly flush. So when I enlarged them and drilled them out, I put a 20 millimeter long screw with a lock nut or a nut jammed against the bottom. Then a pair of nuts jammed together is at the proper. So whenever I put the nut on top here, this is the proper height for the wire wrap socket to go down and enter the dip socket. Since I was able to use a standard off-the-shelf board, I'm going to label the holes alphabetically. I did shear off the end of the board and these diagonals. I've installed a limited number of components on the daughter board. I installed this resistor and this resistor in this pot. I've installed this diode and this diode. I've placed the voltage regulators with heat sinks where they should be. I was trying to establish these 4 positions. And they are these 4 leads right here. Now, the daughter board's connected to this board through the pins on the integrated circuit and through these 4 holes. Here, 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 and here. And then the pins on the socket here. I was forced to print this one in black because of Epson's stubborn reluctance to accept my non-Epson cartridges. I'll reiterate the 4 wire leads. There we go. Are here, 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 and here. And these leads are actually just the component leads from the components I installed on the board. These are 2 American-made diodes. I positioned the diode fairly close to the holes and merely bent the lead straight down through. These represent unregulated voltage, positive and negative, from this pair of full-wave rectified power supplies. These leads go down and tie to the regulated output. And these leads are merely the leads from these 10K resistors. Here, here. And then you see this diode actually connects from here to here. And I just did that connection across the top of the perf board. At this point, I've got all the components mounted on the board. I'll make some corrections to both this drawing and the other one as to exact hole positioning. I mean, these holes, and of course these holes are correct. These holes, this hole, these, this, sort of up to you, but I'll show you the way I did it. One more piece of housekeeping to take care of. This is the board I'm using as a base for this power supply. Was intended that it use an LF353, which is a dual operational amplifier with a split rail power supply. So inside this op-amp package are two op-amps, both powered by one split power supply. I am using one of the operational amps. According to the data sheet, it's B, which means that this thing has another operational amp powered up because it's powered from the same split power supply. 4 and 8, pins 4 and 8. And something has to be done with that other operational amplifier, at least according to most people that do this. And that is, connect the output, pin 1, for operational amplifier A. Connect the output, pin 1, back to the inverting input, pin 2, and connect the non-inverting input to the common of the power supply. Well, the common of the power supply is pin 5 in our case. So that means connect 3 to pin 5. The best place, I believe, to do that, and pay no attention to the wiring down here, is to do it on the wire wrap pins themselves, about halfway up. So this little doohickey ties pins 1 and 2 together, and this little piece of wire here ties 3 and 5 together. Well, so much for poor planning. I had checked to make sure these capacitors, when installed, proud like these are, instead of dead, would clear the underside of the circuit board. I didn't allow for a lot of wiring on the bottom of the board. And so it looks like I have to lay them flat. Well, this is the tracking supply powered up. It's under about a half an amp load. That is to say, the load is equal on the negative supply and the positive supply. Positive output is 1038. Negative is 1038. Tracking pretty well. Five, 8, 9, 6, 5, 8, 9, 4. Two, 3, 7, 9, 2, 3, 7, 6. Eight 15, 8 15. We're near 10 volts now. 10, 11, 10, 11. $11.80, $11.69. It's not too good. $15.30 on the positive. $11.80. It looks like the negative has reached a limit, a plateau, if you will. Now let's look at the schematic. This is a conventional 317 power supply. The voltage across this resistor is going to be 1.25 volts. All the time, anytime. This resistor is adjustable, and the voltage across it is therefore adjustable. By adding these two voltages together, we get the output voltage. Well, that's okay. I'm varying this resistor, this one down here. I'm increasing the resistance, which increases the voltage, which increases the output voltage. And as long as I continue to do that, and I have sufficient input, the output will track up until around 30 volts, and then we get beyond the capabilities of this device, or maybe the power supply. This is a tracking power supply. Again, the voltage across this resistor will be 1.25 volts. The integrated circuit, the operational amplifier, is configured such that whatever voltage is here will be here. And that voltage will be provided by the operational amplifier. As this voltage increases, this voltage increases. Why did it therefore quit around 10 volts? Well, this operational amplifier is being powered by a plus minus 12 volt supply. That's called a plus minus 12 volt supply. Let's look at a specification sheet for the LF353. According to this, the output voltage swing, which would be this output voltage, if it's powered with a plus or minus 15 volt supply. Remember, we're only powered with it plus or minus 12. The output voltage swing at best would be 13.5. In other words, this output voltage is not capable of getting closer to the supply voltage than about 1.5 volts. We're powering it with 12 volts, plus or minus, which means the output voltage could not be more than, say, 10.75 volts. So what's happened is, as we increased this voltage here, this tried to increase equally, but it hit a ceiling, so to speak. Let's say 10 volts. Well, we take that 11 or 10 volts, add 1.25 volts to it, and don't we get around 11.8? So, if you want a plus or minus power supply that goes no more than 10 volts, this is fine. Except for the fact that these things right here are getting extremely hot. These are not hot. These are hot. So I'm going to redo this in another video. I'll finish the drawings for this based on what I have here today. I may check on this LF353. Maybe I'll make the modifications. Anyway, I'm not putting this to bed, but I think there's a better way to do it now that I've actually experienced it. So that's going to be the end of this series, but not the end of this amplifier. I'm going to keep dogging this. Thank you.